All right, so here we are starting second semester, chapter 12, which has to do with the rate that chemical reactions take place. And that turns out to be a really important topic for a lot of different chemistry, okay, and a lot of different aspects of chemistry. In particular, a lot of industrial chemistry and a lot of things like that, where how fast the stuff can be produced is an important limiting factor. One of the big areas of history, one of the big issues of plant growth has to do with nutrients that they have. Fertilizer chemistry in particular has been an enormous important area throughout history, being able to produce fertilizers to keep plants growing and those kinds of things depend on a lot of chemical reactions and a lot of chemical kinetics. So what we have is a group of three sisters who live on a farm, and they obviously have a pretty good crop of plants growing here, but they need to make sure that they can have enough fertilizer to keep those plants growing, okay, so that they can make enough food to support their family, or perhaps their cow. What we want to think about as we go through this is we want to think about trying to understand what drives the rate, the speed with which chemical reactions take place. To do that, we have to think a little bit about what happens in a chemical reaction. What is the physical process? And the key part of a chemical reaction is particles have to collide. The particles have to hit. Okay? So, we need to think about what affects how the particles, the molecules, hit together. And we already have some ideas, you have some knowledge about this. If you think about gas laws, remember our kinetic molecular theory about gases and how they behave? What changes the number of collisions? Temperature. Temperature is a huge driving factor for the number of collisions because the temperature controls what? Kinetic energy, which is the velocity, the speed with which the particles are moving. Higher temperatures mean the particles are moving faster. So temperature and concentration, the number of particles in a given area, are what determine the number of collisions. And fundamentally, it is the number of collisions that's the number one most important factor. How many collisions are there? Okay? So at higher temperatures, the particles move faster. They hit more often. Okay? And there's some other more subtle effects about the energy with which they collide that we'll get to in a little bit. But before we get there, we need to have a mathematical understanding of what we talk about when we say the speed of a reaction. I mean, we can talk about in qualitative terms that the particles are hitting faster, so the reaction's going faster, but we really want to be able to mathematically predict what will happen. How fast will some substance be used up? How fast will our products be produced? And how does that depend on temperature and concentration? Okay? So what we need to do is we need to define what is the rate of the chemical reaction. We define the rate of a chemical reaction as the change in concentration. Remember, our delta represents change in. We use the square brackets. Again, the square brackets are used to represent the concentration, typically molarity, of the substance in the square brackets. So the rate of a chemical reaction is the change in the concentration divided by the change in time. So how much does a concentration change divided by what amount of time did that change happen in?
Why is temperature a factor in the rate?
So temperature is a factor. And we are going to look at the math that describes this rate. But before we get to that point, we need to define what is the rate. So the rate in terms of what we measure is the change in concentration over the change in time. And then we're going to look at how do other factors like concentration and temperature change the rate at which the reaction is taking place. Yes, for most of our experiments we assume the volume remains constant, but changing the volume would also change the concentration over time. But yeah, for our purposes for now, we're not going to worry about any kind of volume change effects. All right, so typical type of reaction, okay? Straightforward reaction. We have NO2 reacting with itself to produce NO and O2. So, we have two NO2 molecules reacting to produce two NO molecules and one oxygen molecule. We can define the rate for this chemical reaction as the change in the concentration of NO2 divided by the change in time. So, it doesn't really matter which one of these we use. So Brandon's question was, do we always use the reactants? No. We use what's easy to measure because we can relate the change in the NO2 to the change in these other guys. Right? So this rate, we say the rate in terms of NO2, the rate in terms of the concentration of the nitrogen dioxide. We can talk about that rate. It will be negative. We put a negative sign on it because we will use up the NO2. So we talk the rate of change is always expressed as a positive value, even though it's actually decreasing. That's why we have to add this negative sign. So we put the negative sign here because we're using up the NO2. How would that relate to the rate of formation of NO? In other words, for every one of these that I use up, how many of these will be formed? Well, it's a 2 to 2 ratio. So that means it's a 1 to 1 ratio. So for every one NO2, I will make one NO. So the rate of change in terms of NO will be the same number, but opposite in sign, because I'm producing NO. So I can relate the rate in terms of one compound to the rate in terms of another one by looking at the balanced chemical equation. Because this is all based on a constant volume, so we're just looking about the change in the number of moles. Now, however, if I look at the oxygen, for every 1 mole of NO2 that I use up, how many moles of oxygen do I get? 1/2. I get 1/2. Remember, for every one of these, I will produce half of an oxygen. So now, because in other words, if I have 2 of these, I produce 1 oxygen. So you divide each side by 2. Now, here's where it gets a tiny bit tricky. You got to think about it. If I want to set the rate of oxygen equal to the rate of NO2, if I want to put oxygen in here, what do I have to multiply that rate by to make them equal? I have to multiply it by 2. Because the change, this delta oxygen value, the delta concentration for the oxygen gas, is this number here is half what this number here is. Okay, the oxygen value is half what the NO2 value is. So I have to multiply the oxygen value by 2 to make this equal. So you can see that it doesn't really matter which one of these we use because we can convert from one to the other. You just have to specify what value you're measuring. And so what value you measure depends, it's all just about what is easy to measure in your experiment. Which one of those products or reactants can you measure? And then once you can measure it, you measure the change in its concentration over time, and that will give you the rate. Now, the rates that we're describing here are what we would call average rates. We're taking the average change in concentration over time, okay? But frequently what we want to know is what we call the instantaneous rate. And that instantaneous rate is what is the rate right now at this point in time. Okay? Essentially, as the time you shrink that delta t value down, okay, until it is at one particular time, at an instant in time.
For the average, can all the delta P's be the same for the three of them?
Well, typically what we're talking about is, if we look at this, one of the things we might do is if we graph concentration versus time, then this starts to make a little more sense. So what we can do here is we can say, all right, excuse me, here is a graph of the concentration. The green line here is the concentration of the NO2. The blue line is the concentration of NO, and the red line is the concentration of O2. So we can describe the rate as the change in concentration divided by the change in time. So if I'm talking about the change from this point to this point, okay, that is an average of these values. You can see if you imagine drawing a straight line between those 2 points, okay, you're getting the average of all those values. But if I want to know what is the rate at 100 seconds after the reaction has begun, I ain't talking about the rate at that time. The delta T is actually 0. I've shrunk it down till it approaches 0. So what I do is I want to say, okay, if I want the instantaneous rate at any point along this curve, that's going to be equal to the slope of the line at that point. The slope is going to be the rise over the run, the concentration over the time. So if I want to find the instantaneous rate at time 100, I draw a line tangent and I calculate the slope of the line at that point. That would be what we call the instantaneous rate. That will be the rate at that point in time. Now, one of the things that's really interesting about this, okay, one of the things that I want you to notice here is as the concentration of the NO2 goes down, the concentration of the products goes up. That makes sense. We're using up reactants to form products. But if you look at the shape of this line and the shape of this line, they are mirror images because it is a 1-to-1 ratio. Right? The slope at each point here is going to be the same value but a opposite in sign because the change in the concentration is directly related 1-to-1 ratio here. Now if you look, however, at the slope, the shape of the oxygen line, it is not as steep. It does not reach, it's not the same slope as the NO2 line. In fact, the slope of this line is half the slope of the oxygen line. Excuse me, the oxygen is half the slope of the nitrogen monoxide, NO, because it's a 2-to-1 ratio in our balanced chemical equation. So we produce oxygen at half the rate we produce nitrogen monoxide. Okay? So those same relationships that we saw, the same relationships that we saw mathematically, of course, are also reflected in this graph. Because what we really want to get at in order to predict what's going on is we want to be able to predict these lines. We want to know what's the equation that defines these rates. Okay? We want to be able to take and model mathematically this reaction. So, same reaction that we've been talking about. NO2 goes to NO plus O2. We want the mathematical equation that gives us the rate relationship to concentration, to temperature. Those are the kinds of things we want to get. Okay? We're first going to look at sort of a little bit simpler case, which is at some constant temperature. Okay? Changes to temperature turn out to have a lot of different impacts. We'll deal with those later on. We're going to focus on looking at concentration right now. How does the rate of the reaction depend on the concentration of the reactant? The more particles there are, the more collisions they will be. The more collisions, the more reactions. Because reactions happen when molecules collide. So, we have a couple of things here, right? We have rate, and we have K, which is a constant, some proportionality constant. It's not a universal constant like the R value. It's a constant that depends on the chemical reaction and the temperature. This is where temperature has its impact, is in this K value. Okay? For our purposes right now, we're going to deal with constant temperature. So the K value is just going to be something we're going to determine empirically by looking at the other concentration information. Here we have the concentration of our reactants. We're assuming that this reaction happens in one direction only, that it goes from reactants to products. Next unit, we'll start to say, hey, what happens in the much more realistic situation of the reaction can happen backwards and forwards? And we have to balance two of these reactions at the same time. And we say N is what we call the reaction order. Okay? The order of the reaction essentially tells us how important, how big of a factor is this reactant in the overall rate of the reaction. For our purposes, the reaction order will be integer values for the most part, although you can have fractional values. We almost always will only see integer values. And they're typically values of 0, 1, or 2. Okay, 0, 1, 2. Those are the typical orders. So we can have a reaction that's first order, second order, or zero order. First and second being, and zero, those are the three that we're going to see. Other orders, while possible, are extremely unlikely for reasons that have to do, that we'll talk about, with how the collisions have to happen. So, reaction order, and this N value and this K value, this is our rate constant. The units of the rate constant will depend on the N value, because the rate constant is going to have units that make this work. We know the units for the rate. That's molarity over time, which is moles over liters times multiplied by time. Okay, and we'll see that in a sec. But the K value has to have units that balance out whatever the concentration units are. So we said that the rate, right, of our NO2 was equal to the rate of NO, which is equal to 1/2 the rate of O2. So we described these equations. We could express the rate of this chemical reaction in these different values. It doesn't matter which one we use. Okay? It will work out. We can use any one of these values, as long as we are clear on which one we're using. So, what we need to do is we need to be able to empirically, that is from experimental data, figure out this rate law. We need to be able to figure out K. We need to be able to figure out the order of the reaction. We need to be able to calculate those things so that we can make sure that we're producing the fertilizer fast enough so that they can grow their plants. Okay? There are a couple of different methods, experimental methods for doing this. The first one, the most common one that you need to know, is called the method of initial rates. So, in the method of initial rates, you will be given some experimental data, or you will go and collect experimental data, which we will do. So, here is our experimental data. Okay? The girls conducted 3 trials based on the reaction of ammonium with the nitrite ion to produce nitrogen gas and water vapor. So, we have 3 trials, and what's different between the trials is the concentration the initial concentration of the reactants. So the initial method of initial rates, this is the initial concentration. And then the rate is how fast this reaction is taking place. And you can see here, they give us the initial rate in moles per liter second. Okay? And the problem would specify, what is that measuring? Like that could be the rate of production of nitrogen gas, or it could be the rate of consumption of ammonium. It doesn't matter as long as we're consistent and we know what it is so we can report that value. So we have a rate and we have concentrations. What we need to think about is, based on this chemical reaction, what would the generic form of the rate law? The rate law is the rate equals K times concentration stuff. What would that generic form of that rate law be? Again, we remember, hey, I need to look at the reactants. Okay, so the rate is going to be equal to the rate constant K times the concentration of the ammonium raised to some power times the concentration of the nitrite raised to some power. N and M are not related to the coefficients. Okay? For rate laws, N and M are not related to the coefficients here. You can't look at the coefficients and figure that out. You have to use experimental data to figure out what's going on, for reasons that we'll talk about later.
So what's the difference between N and M?
They're two different variables. We got to figure out what they are. Right? They could be, each one of them is going to be some number, probably 0, 1, or 2. The method of initial rates is based on looking at ratios of the different trials, where we pick which two trials we want to put into ratio so that stuff cancels out. You'll notice that I have essentially 3 variables here, 3 unknowns. So I'm going to need to use at least 3 equations to solve this. Okay? And that's one of the reasons why I have 3 trials. So, we want to go through here and I want to explore, I want to look and say, hey, look, in trial 1 and trial 2, the concentration of the ammonia is the exact same. So if I set up a ratio between 2 of these equations, the ammonia value will drop out because it's going to be the exact same. And that's how I go through and look and do this. I look into the data, I look into the concentrations, and I find one where one of the values, or all the values but one, depending on how many values you have, all the values but one stayed the same. Here I can see that my concentration for the nitrite doubled. So I can set up a rate. I'm going to say I want to take rate number 2 divided by rate number 1.
So when you find the values but one, do you cancel that one out?
No, well, I have to set up a ratio to make them cancel, right?
Oh.
They don't just cancel. I have to set up the ratio. So that's why I'm doing this. I'm saying experiment number 2 divided by experiment number 1, the ammonium should cancel out. And I would encourage you to put the value that is larger concentration of the thing that's going to stay on the top, because most people have more difficulty working with fractions and exponents than they do with whole numbers and exponents. So I'm going to put rate number 2. I'm going to look up the value and I'm going to stick it in there. And I'm going to look up the value for rate number 1 and I'm going to put it in. And then I'm going to write the rest of the equation, right? I'm going to have K for experiment number 2. And I'm going to have the concentration of the ammonium raised to the power n. I'm going to have the concentration of the nitrite raised to the power m. And I'm going to do the same thing for experiment number 1. I'm going to have the K value, the concentration of the ammonium, the concentration of the nitrite. And I built this ratio specifically so that things would cancel out. I know that the K values should be the exact same. So k on the top cancels k on the bottom. I don't know what this value really is, but I know that the value will be the same on the top and the bottom. 0.1 raised to the n power is going to be the same as 0.1 raised to the n power. So that cancels out as well. So now I go through and I can divide these out. 2.7 times 10 to the negative 7th divided by 1.35 times 10 to the negative 7. What's that? It's 2. So I divide that out and it becomes 2. So I have 2 equals 0.01 to the m power divided by 0.005 to the m power.
So how did you get 2 again?
I divided 2.7 divided by 1.35. So, if I have this, is there a way I can simplify this? How can I do that? What am I going to do? I can group these m's together, right? I can say that what's 0.01 divided by 0.005? That's 2. So this is the same as 2 to the m power. M has to be 1.
So you're always solving for m?
Well, in this case I solved for m. Now I need to go back and solve for n. And once I have both n and m, then I'll need to go back and solve for k. So, if I wanted to solve for n, what ratio should I set up?
2 to 1.
So I just did 2 to 1.
Oh.
That didn't the n's canceled out. I want rate 3 to rate 2. The m value, the nitrite value, stays the same. The ammonium, our n value, is going to double. So go ahead and set that up. Do that right now. Find out what is n. I want you to go through and solve for n. we go through, you want to set up this ratio, right? Rate 3 to rate 2. You actually look up the value for rate number 3. You put in the value for rate number 2. You have your K value, the concentration of the ammonium, the concentration of the nitrite. You do that for rate number 2 as well. And again, the K values cancel out. In this case now, the nitrite values cancel out. And you're left with your value. You divide these, you get 2, 2 to the n. N has to equal 1. Okay? So we can say that the rate is equal to K times the concentration of the ammonium multiplied by the concentration of the nitrite. So this is to the first power to the first power. That's what we just solved for, N and M.
Wait. How do you know which concentration you're using?
You look at which rate you're using. So rate 3, we went to.
That was just for the general input, like for the whole.
So this concentration here, these are variables that are going to change. Now I can go through, once I solve for K, and I can plug in any concentration of ammonium and nitrite, and I will know what the rate will be. I've just described a mathematical equation that defines how this chemical reaction behaves. Once I know what the concentrations are, I can substitute them in and solve for the rate now. How will I find K? How will I know what the value of K is? What am I going to do? Yeah. Pick any one of these equations, or all 3 of them. Plug in the concentrations, plug in the rate, solve for K.
And they all come out the same.
In this case, this is a theoretical perfect example. They all come out the same. In the real world, they won't all come out the same, and you'd average them.
So we would have to just further in this chapter, we have to average.
Yeah, when we do our experiment. Okay? So do that. Tell me, what is K? Go through, solve for K. Should only take a couple of minutes. Did you get your K value? 2.7 times 10 to the negative 4th. Now, what are the units? Okay, what are the units? So we got it. We know it's going to be 1 over seconds. We've got to have the 1 over seconds in there. But notice, remember that I have 2, this is moles squared over liters squared. I want one of the moles and one of the liters to cancel out. I need, because that's too many. My rate is moles over liters times seconds. So my K value is going to have units of liters over moles multiplied by time, or seconds. That should be an S. So remember, what we had is we know that the K value, or the rate, we want the rate to be moles over liters times seconds. That's my molarity divided by seconds. Molarity over time. That's the units. So this is my K value. Here I had two concentrations. So that's moles over liters and moles over liters. That's too many moles and too many liters. The units won't work. So my K value has to cancel out one of the liters and cancel out one of the moles and bring in the seconds. Right, so let's say that this had turned out to be second order. Then this would be squared and squared. And what if this had turned out to be zero order? That goes away. They're just ones. So here, this would go away, and it would just be 1 over seconds. Okay, so you have to look at what are the units for your concentrations. That's going to give you the units for K. Because we always want it to be moles over liters times seconds. Yeah, and they can have 3 reactants. So yeah, crazy stuff. Okay? So, method of initial rates, you go through, you set up a ratio so that stuff cancels out, allows you in one step at a time to determine what are the order with respect to each reactant. Once you have all the orders, you pick one of the experiments, you substitute its values to solve for the rate constant K. Not chemistry, it's chemistry, they're called orders. Of course, in math, you would call that the exponent. Right? We call it the order of the reaction. But it is mathematically an exponent. Okay? So we know how fast we can produce the nitrogen to feed the plants. But we need to be careful. We're going to have to think about this a little bit more. We need to know how does the we can now describe how does the rate change with concentration. But what we're going to want to do in the future is how does the concentration change with time. Okay? For anybody thinking about calculus, we're talking about some integrals and derivatives. That's really what we're doing here in a sort of very simplified way. All right, you have some homework for tonight.